So here's some more on linear systems and invertible matrices. Most of this stuff is I already have written down just because I've already made the video once, only to find out that it stopped recording after 50 seconds. So here we go. If A is an n by n, this is a theorem. If A is an n by n invertible matrix, then for each n by 1 matrix B, the system AX equals B has exactly one solution, namely X equals A inverse B. Again, this is something that you probably don't find too surprising. This is the way it should be. But here's the proof. First of all, we want to note that A inverse B is a solution. So I plug it in here. A times A inverse B does equal B. So this is a solution. Good. Now, suppose we have some other solution. The thing is, I said there's exactly one solution. So I found at least one by showing here's one. So suppose I've got any solution. A solution to this system, right, where A is the coefficient matrix, B is an n by 1 column matrix. So if this is a solution, then when you plug it in, A times x0 should equal B. That's a true statement. Well, if that's a true statement, then multiply both sides by A inverse, and A inverse exists because we said that A was invertible. So A times A inverse is just I times x0 is just x0, and you end up with x0 equals A inverse B. So if you had any solution, it's the same one that you already had. So if A is an invertible matrix, then the system of n equations with n unknowns always has just one solution. Okay. Now, another situation that we may find ourselves in from time to time is looking at several systems that all have the same coefficient matrix, but they have different constants over on the right-hand side of the equations. This a situation like this would be when we start looking at matrix multiplication as defining a transformation, that you have X as an input and you multiply it by the matrix A to get some output. And then the question of what's the range? What kind of outputs could you get? Could you get B1 as an output? Could you get B2 as an output? Could you get B3 as an output? Each one of these is a separate system where you're trying to solve for the input variables to make sure that you can actually get this output. So in the event that A is an invertible matrix, it's really not too hard to see that the solution is just A inverse B1 or A inverse B2 or A inverse B3. I mean, that's easy enough to see. But when you think about what does it actually take to do the computation, well, if you're starting off with a system, you know all the numbers, all the coefficients here, the entries in A, you got to find A inverse. And then you've got to do the matrix multiplication times B1. Likewise here, well, you've already found the inverse if you did it over there, but then you got to multiply by B2. How do you find an inverse? Well, you find an inverse by setting up a big, matrix where you have A and I next to each other, right? You have this A, I, and then you put that in reduced row echelon form. Well, or you could just say, well, I don't need to find A inverse. I can just solve the system by doing something like this, doing A, B1, and putting that in reduced row echelon form. Or, then to do the next one, you say, well, okay, then I'm going to do A, B2, and then put this in reduced row echelon form to see what the solutions look like. Well, notice that in each one of these cases, whether you're doing this or this or this, that you're putting it into reduced row echelon form, it's all being determined by this matrix A. What are the row operations that you need to do? Whether you do them here or here or here, you're going to transform A into its reduced row echelon form, which if A is invertible, we already know will be the identity matrix. But if it's not invertible, well, this is not going to create an inverse, but this will still solve the equation, solve the system, and this will still solve the system. But essentially, you're doing the same row operations here, or to do it for this one. So it's like, why not just do it all at once? Solve all the systems at the same time, like this. all the systems at the same time by making this big matrix here with A right here, and then B1, B2, B3, and then put this into reduced row echelon form. Okay. If A was invertible, then you'll get an identity matrix here, and you'll get the three separate solutions here, in these places. However, it's also the case that if A is not invertible, you'll be able to solve for the infinitely many solutions because you'll have zeros here, probably a whole row of zeros. If it's not a whole row of zeros, if there's a 1 in one of these places, then you know that for that value of B, there's no solution. But if this is a whole row of zeros, then you can get the infinitely many solutions for each situation. Let's do an example. So here's 3 systems that all have the same coefficient matrix over here on the left, same left-hand sides of all the equations, but different numbers here on the right. So what I'm going to do is I'm going to make one like extra large augmented matrix. So I've got 1, 2, 3, 2, 5, 5, 3, 5, 8. That's the coefficient matrix. Now I'm going to use the numbers here, 7, 14, 19, down here, 7, 12, 19, and these 6, 12, 16, and put the whole thing in reduced row echelon form. And I'm going to just let my calculator do that. So I'm going to pause just for a moment and then come back when my calculator's done. So I'm back, and this is what it looks like. The first 3 columns look like an identity matrix. So apparently matrix A was invertible. That this coefficient matrix here, actually I should say this matrix, just those first 3 columns, is an invertible matrix. So each of these systems has only a single solution, and the columns, the last 3 columns look like this: 2, 1, 1, 1, 0, 2, and 1, 1, 1. What that tells me is that the solution to this first system, slide up. The solution to the first system is x1 equals 2, x2 equals 1, x3 equals 1. That's this column right here. Okay. Then, actually, I should do this because I can do it. There's this laser on this thing. I can say, I want to do, never mind, done. So this 1, 2, 1 comes from this column right there. See, and then it goes away. Cool, huh? Yeah.